I thought you were gonna change it back. Like I was like, I think you do. I thought no. I went on to like this generator that makes text. I was like, yeah, like it has a whole word there and snap fast.
All right. It's Friday. Sure. I think some of you had a reprieve. City college exam today. Right? Be glad you're not in that class. All right. Exams. Those are graded. So I don't know if I released the exam so you can see it. Let's check there. I think I did, but I could be mistaken. So under the quizzes and exams, I have the keys. So the R markdown key, and I posted the wrong ones. Those are the RMD files. So, I have the PDFs. I don't know why the PDFs weren't uploaded. I'll upload the PDFs so you have them. And then the theoretical knowledge. Check my test options. All right. All right, that test is now available. So you can check the answers, what you got right, what you got wrong. I'll upload the PDF of those keys. I don't know why I did the RMD files. No idea. But check them out. If you have questions about an answer that maybe got kind of wrong or something like that, please email me. Double check if that is the actual RMD file. Yep, of course. Yep, it's an RMD file, and the problem is that if you try to run it, it'll probably fail because it's in reference to where I've saved all of my files. That's why I do the PDFs. So I'll get those uploaded. The other thing is the homework. Over. So I don't know if you saw the keys. They're up. I had mentioned a homework assignment. Undo the edit. So I have posted number 8. So I put the due date TBA. There is this other homework 8 extra. This was one that we would have done by hand, but we're not doing it by hand. So what I've done is just created a whole new assignment that allows you to kind of practice the standard errors, confidence intervals, and so forth. I don't have a due date on it just yet. We need to get through our confidence intervals. All right, and that includes our parametric confidence intervals and our bootstrap confidence intervals. So we'll make that due at some point. Also stripped off, I know there's other dates on these, but we haven't made it there, and our dates are going to be off. So I do think this homework number 8 is probably going to be due on Monday. That gives you the rest of the lab to finish it out. And then this hypothesis testing and CIs, you're going to see it that it is, oops, that was number 8. Sorry. The one sample tests you're going to see is a lot of like choosing what test to run. And what we'll do is we'll break this up into like 2 different due dates. So the first due date is just going to be like before our next class. We have to go through and answer like all of the A's. So that way everyone's on the same page as to what test to perform. All right. And then like the next class period would be the rest. So we'll get there. All right. So we have confidence intervals of means. All right. This is the parametric confidence interval. And it's a parametric confidence interval because we assumed normality of our data. All right. So we assume normality, which then allows us to use that t statistic or that t table. All right. Because when we assume normality, then our x minus x bar over the standard error approximates a t distribution. All right. So this is our parametric version of our confidence interval. And we worked through it. I showed you how to do it by hand, but then we really showed you how to use R to get that t, to generate our standard error, and to get the confidence intervals. And this is where we left off. So if we wanted to improve our confidence, make the interval narrower, all right, we have 2 options. One is to decrease our standard deviation, all right, and that's really not going to happen. All right. Normally the site, I should say, is not going to happen. Normally it's not going to happen because usually your measurements are such that that error is already minimized. All right. But if you do think there's measurement error happening and that's on us, then we're going to have to fix it. This is one of these reasons why some of you doing research, some of the very early data collection points, we just tend to throw out because that's kind of you getting used to taking the measurements and getting down precise. At least that's kind of what we do in the lab. The other way is to increase our sample size. And the reason both of these work is because what we're doing is trying to lower our standard error. We're trying to decrease that standard error. We do so by decreasing S, which we probably don't have any control over, or we increase our sample size. All right, so how do we report the error? We said reporting our error, we're going to usually report the standard error. In a few cases, we'll do the standard deviation. Very rarely, we report our error, our confidence interval in this format. Normally, our 95% confidence intervals or whatever percent confidence intervals are going to be included as part of a figure, or we'll give a range. All right? So normally it's going to be this way. X bar plus or minus the standard error, or we write the mean, and then we give standard error in parentheses. Now, how do we report it? How do we round it? Well, we do have a general rule for this. All right? We have a general rule. And that rule is to take our standard error that we calculate, right, the unrounded standard error, and we divide it by 3. All right? The first non-zero digit that we get when we do that division, that is where we round our statistics. So that's where we round our mean. And then our standard error goes to one more level. All right, goes to one more level. So here's an example. Just pull the board and make sure that it looks good. All right, so let's just say we have an x of, I don't know, 2.12.3469. All right, random number, all right? And let's say we calculated standard error as 1.88543 repeated, all right? Something like that. Our rule, general rule, is to take this standard error divided by 3, all right? So divided by 3. You can use your calculator. I'm going to do it just longhand to demonstrate it, all right? So 0, right? Then 18 is 6. Well, there's our first non-zero digit, all right? It's at this spot, the tenths place, where we report our mean. So it's 12.3. All right? 12.3, that's where we round based on this rule, the standard error divided by 3 rule. And then our standard error goes to one more digit. So this is how we would report our mean and standard error. Pretty simple. Now, usually what happens, and I know we talked about rounding measurement values, and we said anytime we calculate the mean, we go to one more digit than what we actually measured, right? So if we counted offspring, right, that's a discrete number. We've counted whole numbers. When we calculate the average offspring, we go to one more digit, which would be tenths, all right? Usually, if we found the standard error of the offspring, it would probably get us to this spot where we report the mean as tenths and the standard error to one more digit. Usually, not always, but usually. All right? So with our standard error, when we report it as if we're reporting it in a paper, we have to use, or we should use, this rounding. This rounding. Easy? Simple? All right. Do we need to practice some of this? It's on our homework. I say report it as if you're reporting it in a paper. That means we need the rounding. All right? Any questions? We will always be doing that. All right. What about graphics? So this is it if we're reporting a text. All right. That's if we're writing it in a text form, we're reporting mean and standard error. What about graphical methods? All right. So normally our graphs are going to have the means on it, and then we have to have some measure of dispersion. All right. So that's measure of dispersion, standard of deviation, or standard error. Usually going to be the standard error. All right. Sometimes you can do this confidence interval. I'm going to say it's rare if you have regular measurement variables, but at least in parasitology, we do report confidence intervals much more frequently because we're reporting percentages. And for percentages, it makes a little bit more sense to report confidence intervals. But it's going to be the same type of deal. You're going to report that measure of central tendency, and then you're going to add error bars to it. All right? So how do we do that? Well, it just kind of depends on what kind of graph we're making. All right? So bar graphs, remember, just for frequency data, we'll add our whiskers as part of the standard error. And this would also apply if we did XY scatter plots or if we made line graphs. All right? And each one has a slightly different reason, slightly different purpose. All right? Box plots are already built into R. So these bar graphs, yeah, we can make a bar graph in R, but Excel does the bar graphs for us, and that's probably where you added these whiskers, and it's probably made the graphs incorrectly because you shouldn't have used the bar graphs in the first place. But what about box plots? Where are my box plots? There it is. Ah, I can see it. All right, if you want to do this as practice, we can. If you don't, we can move on. I guess I forgot this slide was coming up. Do you want to practice rounding? Hold on, you say yes? One person says yes. All right, let's practice it, and then we'll get to box and whiskers. I pointed you out. I pointed you out. All right, so yeah, before we get to box and whiskers, here's some practice. 3 practice. You can use a calculator. You don't have to use long division to do this. Just look for that first non-zero digit. That's where we round our mean, and then we do our standard error. And I think as you do that, I'm just going to use R, open up RStudio. Do this. Don't forget our regular rounding rules. Round up, leave it the same. This also apply here. Get 'em. Get them all 3. Oh, grab the wrong title bar. Here's my R. There it is. Yep. The reporting standard errors. These are rounding rules. We're going to divide the standard error by 3. We could also divide the standard deviation by 3 if we're going to report the standard deviation. But for our standard error, since that's going to be so common, we divide that by 3. The first non-zero digit, that's where we round our statistic. We go 1 more digit for the standard error. So first up, 0.8943, that's our standard error. I divide by 3. First non-zero digit is the tenths place. So that's where we round our statistic. We go 1 more for the standard error. All right. Next one, 2.39. Divided by 3, we get 0.797. First non-zero digit is the tenths place. So we round our statistic to the tenths. Our standard error goes 1 more digit. And then lastly, standard error is 10.22 divided by 3. Our first non-zero digit is the ones place. So we round our statistic to the ones digit. So 495, nothing after the 5, so we leave it alone. Right, plus or minus 1 more digit. All right, so I just kind of did that in R. And hopefully easy. And here it is. Here it is on the presentation, just kind of the same thing. Did the arrow, this is where we rounded. Right, this is where we round our statistic, and then our standard error goes one more digit. All right, not terrible. All right, there was going to be one more thing I said. I can't remember it. Maybe I'll think it. Maybe I'll think it. All right, so getting back to our graphs. I'm going to show you a box and whiskers plot. All right, box and whiskers. This is going to be a preferred method. It doesn't have to be the method that you choose, but it's a preferred method of displaying central tendency. All right. This code that I have up here was used to generate this box plot. All right, so I set the seed to 3. I made a y1 and a y2. All right, I then repeated a and b for an x variable. All right, I capped our y's, so I concatenated them. So I've got one column for the y's, I have one column for my x, and then I did a boxplot y as a function of x. We're going to rarely do this. I present this here just for this figure. Normally we have the data set up like this already from Excel. So we input our data into Excel, or I gave you the file. Now, why does Boxplot one of the preferred methods? Because it illustrates multiple points. It illustrates central tendency, it illustrates dispersion, it illustrates skew, and it gives us an idea of outliers, if we have outliers in our data. So there's 4 things with that. Unfortunately, though, our measure of central tendency and dispersion is all related to the medians. So our central tendency is actually the median, which is the line inside of this box. All right, that right there is our median. The box represents our interquartile ranges. All right, so if we're interested in means, this probably isn't the graph you want to use. All right. But if we know that our data are normally distributed, you can get away with this because our mean and our medians are going to be close to each other. They should be equal, but given randomization, stochasticity, it's possible that we might have slight differences. All right. What about skew? Skew tells us information in the box. So ideally, if we are unskewed, then our median should fall in the middle of that interquartile range. Just like our normality curves. Right? Our peak should be right in the middle of the distribution. Same thing here for skew and the median. Our median should be right in the middle of that box. Right? This one closer to being in the middle. This one off the middle. You can see much bigger box above the median than below, and no big surprise, we did a chi-square distribution, which is skewed. All right, and the last point are the outliers. All right, so these are the whiskers, and our whiskers, hence the name box of whiskers. The whiskers, they don't represent a range. Rather, they represent 1.5 times the interquartile range, or the maximum value. Maximum or minimum value. All right, so in this case, these points on this figure for A represents the minimum and maximum values of our data set. For B, this point down here represents the minimum. This point up here represents 1.5 times our interquartile range. How do I know that? Because we have points beyond that point. All right, so why do they mark it 1.5 times the interquartile range? Well, some of the textbooks, some people would say that if we are more than 1.5 times the interquartile range away from our median, then these are outliers, and we are justified in removing them. My stance is don't remove them, it's possible that you can get some of these extreme data. So leave them in unless you have reason to suspect otherwise. And I know we'll talk about these outliers a little bit later. All right, so we have our median, that's our central tendency. Interquartile range, that's our measure of dispersion. Skew can be visualized based on where we are in that box. We should be right in the middle. All right, and then our outliers are those points that fall beyond our whiskers. And our whiskers represent either the minimum and maximum values or 1.5 times the interquartile range. All right. So this is why I said here with R, or in my note, the R doesn't use 1.5x unless there's a data point beyond that. Then it does go to 1.5x. All right, so how do we make a box plot? The built-in function is Boxplot. That's a built-in function. You could do Boxplot y as a function of x. So you write it as a formula where y is your measurement variable, x is your grouping variable. And when you write it this way, you give it the data frame name. So you say data equals whatever the data frame. So that way we don't have to use our dollar sign to reference the variables. All right. We've told R knows where to look for these guys. If you only had a single variable, you would just give it the variable name, but I don't know why you would do it, why you would make a box plot. If you only have a single measurement variable, it's histograms. Those are the preferred method. All right. And the other way is a lattice package. It's probably not going to be useful for us for this class, but in the graduate level class, it may be useful. Because in the lattice package, we write it as a formula, y is a function of x, but we can add a second grouping variable. So if we were interested in, let's say, fish lengths over, let's say, 3 months, June, July, and August, all right? We would do length as a function of month, and then let's say we did this in 2 lakes. We would say we would do our pipe symbol lake. And what it'll do is do a box plot for 1 lake, and then do another box plot for another lake. Saves us time. Saves us time, makes it useful. All right, any questions on box plots? We're going to be making these. We're going to be making quite a few of these as we get to our hypothesis testing, the ANOVAs basically. All right, so let's say we did a histogram, and it looks like our data are skewed, all right, or non-normal in some way. And you say, okay, I run, let's say a QQ plot, and we can see our data are non-normal. When we report the measure of dispersion, standard error can work. All right? It can work for basically any type of distribution. But if we're too skewed, then what ends up happening is that our standard error gives us a symmetric type of error measurement. But we don't have symmetric data. We're skewed. We're highly skewed. So what we should be choosing then is some measurement, some dispersion measure that reflects that underlying skew. And one of those that we can do is bootstrapping, doing bootstrapped standard errors. All right. Now the bootstrapping procedure isn't very difficult in R. All right. If we did it by hand, it would be next to impossible. We could take the entire weekend for you to generate all your replicates. All right. But in R, it's actually really easy. So what's the benefit of this bootstrapping? Well, we can do bootstrapping on any statistic that we want. All right, we could do it on means. We could do it on medians. We could do it on percentages. We could do it on any type of statistic that we want. We could even do it on like a T or an F statistic. All right, it doesn't matter. And the other added advantage is that we make no assumptions of the underlying data. But our estimates, our standard errors, will reflect that distribution. So if we're skewed, our measure of standard errors will be skewed. Our confidence intervals will be skewed. All right? So how do we do it? And I kind of wrote up the basic premise, the basic process. So first what we're going to do is collect a sample of size n and calculate our statistics. So we go out, we took measurements on, let's say, snails. Snail shell lengths. All right? We have a bunch of those. And then let's say we calculate the average of that shell length. All right, that average is going to be our observed test statistic, ST observed. And I did this generically just to kind of demonstrate that it doesn't matter how we do it, as long as we pick a statistic of interest, in this case the mean. Then what we're going to do is take our data set and we're going to sample with replacement equal number of samples. So let's say I collected 52 snails. Why 52 snails? Because there's 52 cards in a standard deck of cards. All right? So each card represents an individual snail and it has a length written on it. What this sample with replacement is going to do is I'm going to shuffle it up and I'm going to draw one card and write that number down. And then I replace the card, shuffle it back up, and draw a second card. Write that number down, and repeat it over and over and over again until I get 52 cards. Now, sometimes I'm going to draw the same card twice, or 3 times, or 4 times. Sometimes some of those cards won't ever be drawn. This is the basis of bootstrapping, sampling with replacement. All right? Once we've collected our 52 samples, this is now known as a bootstrapped sample, right? Sampling with replacement. Then we will calculate our test statistic. So in this case, the mean. And this is a randomized test statistic. This statistic came from our bootstrap sample. Then we're going to record it. We're going to write that number down off to the side and say, this is our first replicate. And then we're going to go back and redo this process again. Take the deck, shuffle it back up, draw one individual, put it back. Draw a second individual, put it back, and repeat it over and over and over until we get 52. Calculate our statistic, write it down, and then repeat over and over and over again. All right? From that, we have a collection of our randomized test statistics now. Let's say 1,000 of them. And from here, we can calculate a mean, and we can calculate a standard deviation. All right? So the mean is a bootstrap mean. And what you'll see is that this bootstrap mean will actually be pretty darn close to our actual mean. That's the process of, the randomization of large numbers and all that stuff that I talked about. This kind of a central limit theorem idea. All right? The standard deviation is going to be the standard error of our randomized values. So the standard error of the mean is the standard deviation of the mean. All right, now for the confidence intervals, which is what we're really going for with this, we don't need to use the standard error from our distribution. We don't need to use a t-statistic because we have our randomized set already there. We already have that distribution. So what we would do is just take the 2.5% and the 97.5% quantiles of that vector. And that gives us our 95% confidence interval. It says 95% of our bootstrap samples, our bootstrap replicates, fall within this range. All right? So here's an example. All right? Here's an example using fish. We collected 50 fish. 10 of them were infected with the parasite. All right? So 10 out of 50. All right? That means our prevalence, the percentage of individuals that are infected, is 20%. That's just a single number. All right? We can make assumptions and calculate a confidence interval for that, but we don't want to do that. We don't want to make those assumptions. We want to generate it randomly. So how do we go about doing it? Well, we're going to do some bootstrapping. So this is what we're going to do. We're going to do this in R. I have the code. This is the code that I used. And we're going to create our code very similarly. So open up your R and let's start on bootstrapping. This will be Bootstrap Confidence. And this is what we're interested in calculating. All right. So first up, what we're going to do is with this sample in R, we actually need the data vector. All right. So in our presentation, I just kind of said we had 50 fish, right? 10 of them were infected. So what we're going to do is create this vector. All right. We're going to create this vector so that we have it keyed zeros and ones. 0 is uninfected, 1 is infected. So we're gonna make a vector where we're gonna repeat 0 40 times, and we're gonna repeat 1 10 times. All right. So now what we've done is taken the verbal description, all right, and we have a vector now of 40 zeros and 10 ones. Now, why do we do that? We do the zeros and ones because if we take the average of that vector, that gives us our prevalence, 0.2. That gives us the percent that's infected. And you can do this with sex. So key, instead of writing M and F, key it as 0 male and 1 is female. And then when you calculate the average of that vector, that tells you what percentage of your individuals are female. You could do success and failures. All right, same way. All right, so we have the fish vector. All right. All right. Now what we're going to do is do our bootstrapping. All right. So the first thing that we're going to have to do is create some value, some vector that is going to hold our randomized statistic. All right. So what I'm going to do is we're interested in the mean of this fish, right? So a prevalence or proportion is normally P or pi for the population parameter. So what I'm going to do is do P obs. That is our observed prevalence. And then what I'm going to do is call the randomized one P rand. And I'm just going to create an empty vector. All right. And what I'm going to do in this code is kind of annotate it so you can see what we're doing at each step. All right, and I can do that by using the number symbol, the pound symbol, because that says, hey, don't execute the code after this. So our very first line, we're going to create an empty vector, P rand. All right, that's going to hold a randomized test statistic. And then what we're going to do is create a loop. All right, so this is our loop. And the loop is going to be a counter. It's going to have a counter. All right, so I've got 4, and then in parentheses, I in 1 to 1,000. All right, so I'm going to do 1,000 replicates. Normally, anytime we do randomization, we start small and maybe go like 100, because if you messed up the code and you did something, let's say 1,000 or 10,000, or the code's like really long, you don't want to be sitting there for an hour waiting for it to end, only to find out that, oops, I did something wrong and I'm not getting the answer that I wanted. All right, if something takes that long, you want it to be right. You want it to be right. All right, so what this did is, this is the loop to fill out the P rand vector. So this is our loop. Now the loop is marked off by the braces, by the curly braces. So it says we're going to run everything in here. So it's going to run the code, and then when it gets to the end, it's going to jump back to the beginning, and it's going to increment that I. So I is going to start at 1. It runs all the way to the end, and then it's going to jump to the next one and increment I to 2. And then it runs it, and then it's going to increment the I to 3, and so forth, all the way up to 1,000. And then it jumps to the the beginning and increments it up to 1001, and it says, oops, I only want to go to 1000, and it gets out of the loop without running it one last time. All right. So I created my loop. Now, what am I going to do in the loop? All right. Well, we have to make our randomized vector. All right. And I know this is going to be a little bit different than what's in the presentation, but one of the things that I like to do is just standardize how I've called everything. So one thing that I've done is kind of move to rvec as like a randomized vector. All right. So in this, what we are going to do is sample. We're going to sample our fish vector. All right. So we talked about sampling before. That's sampling, and we had sample with replacement and sample without replacement. This one's going to be sampling with replacement. So we're going to sample our fish, and we're going to use replace equals t. So this will be our bootstrapping. And then we're going to save that vector, because this is going to be our randomized vector. Now, we didn't give it a size. We could have. All right, we could have sampled only 10. But we don't. With bootstrapping, we want the same sample size. So however many values we have in fish, that's going to be what we get sampled. Or that's how many samples we draw. Once we have our vec, then what we're going to want to do is calculate the mean of that vector. And this will be our very first bootstrapped mean. We're going to save that in prand. All right? So we want the mean of our vec. All right, so we're going to calculate the mean of our bootstrapped vector, and then we're going to save it in prand. Now in prand, I use brackets, square brackets, and I put the I inside of it. So the brackets is something called subscripting. All right, something called subscripting. What that subscripting does is reference an item inside that vector. So this is a vector, it's just one column. So whatever is specified in brackets is the number of rows. So the very first one, I is 1. So it says we're going to generate our bootstrap vector, we're going to calculate the mean, and then we're going to save it in row 1 of prand. Then it jumps up back to the beginning. Resample our vec, calculate the mean, save it in the second row. Jump back to the beginning, new sample, new mean, save it in the third row. Over and over and over again until we get the 1000th row. This is why we had to create this prand to begin with. We have to create it outside of the loop so that it persists outside of the loop. All right, so I have this set. All right, and I'm going to run it. And it runs actually pretty quickly. And you can run yours too. All right. Now, we created prand outside of the loop, so it persists outside of the loop. Anything that we created inside the loop should be hidden from us. Or at least it usually is. Some things are, I guess. So rvec was created here, and then it just keeps getting recreated all the time. All right, but prand, it kept changing. So now let's do our bootstrap mean and standard error. So mean of fish, whoops, not fish, prand, and SD of prand. So the SD is also the standard error of our means when we do these bootstrapping. I did SD. This is SE. There it is. All right. So 20%. That was our original vector. The mean of our bootstrap vector is 0.1983. That's the mean of all of these bootstrappings. All right. And it's close. I mean, it's going to be close to what our actual value is. It's not going to be exact because of randomization. So what was yours? Catherine, what was your mean? All right. Francisco, do you have it? 0.20154? 0.20. Alex, what was yours? 0.199. So you can see everyone's going to get a little bit of different. Why is everyone getting a different value? Yeah, everyone did a different sample, and we didn't set the seed. If we set the seed, everyone gets the same thing. All right? So that's our mean, that's our standard error. What about the confidence intervals? So our confidence interval is obtained using the quantile function. So our quantile of prand, where our probs is 0.025 and 0.975, we run that. This will give us our 95% bootstrapped confidence interval. So this is my confidence interval. And what does that mean? Is. What does that mean? Increase this just slightly. This is the histogram of our prand, of all of those bootstrapped replicates. And this is the means of those. All right? Our confidence interval is capturing 95% of all of those values. So for me, 0.1 up to 0.3 represents 95% of my values. 95% of my values of all of these values used to make that histogram fall inside of that range, which means I have 5% in my tails. That's what a confidence interval is. That's what our confidence interval is. Questions? When do we do bootstrapping? Any guess? Any guesses? Exactly. When we don't have normal data. So if we are normally distributed and we do a bootstrapping technique like this, our confidence interval will be almost identical to the parametric bootstrapped intervals. To what we would use if we use the t-distribution in a regular standard error. If we are not normal, then we're going to see differences. We're going to see big differences. So we weren't overly skewed in on our data. 10% wasn't that far off. But you can still see my confidence interval around 20%. I'm just slightly higher going high. All right. And that's kind of what we see with percentages. The closer we are to the extremes, the more skewed we're going to be. The more skewed these intervals are going to be. All right, so what we're going to do on Monday is we're going to review bootstrapping again. We're going to have plenty of practice. All right, there is this on the homework, this parametric using the t statistics and this bootstrapping. All right, right now you're going to be writing your own bootstrapping code because once you understand how to do this, then when we do randomization tests, you're going to feel more comfortable about writing the loops and getting our test statistics so we can figure out where our 95% values are. as a little preview. If our hypothesis value is not captured by our bootstrap confidence interval, then we're different. Then we're different. And that test statistic is not possible just from, I should say it's not possible. It's highly unlikely to get that under the assumptions of the null hypothesis. All right, we'll pick this up on Monday. It's a lot. Contemplate it, and then I think we'll do another example. We'll walk through another example for bootstrapping to get you comfortable. All right, you guys have a good weekend.